Hi, y'all. In this lesson, I'm going to cover everything you need to know about rational functions. I'm going to go over 3 examples that I think will give you a really good concept of what you can expect. So, as promised, you can see here on this first page that I've got a really good summary of everything you need to know about rational functions. In some of my previous videos, I've covered domain and range and asymptotes, but now we're going to get into x-intercepts, y-intercepts, everything you need to know, slant, asymptotes, everything. So I put a good summary on this page in hopes that it will help you study and just kind of put everything together as you look back over stuff before you start looking at problems. So remember that denominator is domain. So when you're looking at the denominator of a rational function, you're focusing on the domain. And domain is associated with x values. So we're looking for x values that are going to be excluded from the domain. Those places in the graph where there's discontinuity. And those places are called holes and vertical asymptotes. So you may never have a hole in the function, but you might. So basically what happens for a hole is if once you factor everything out, if something divides, then that's a hole. That factor has an x value with a hole. And then the vertical asymptote is everything left over in the denominator. You're going to have factors left over, set them equal to 0, solve, and that's your vertical asymptote. So those are both connected to domain. Domain is x. So these are the x values that are excluded, holes and asymptotes. And then also with x is the numerator. In the numerator, you're going to have some factors, anything that didn't divide to become a whole, and those are called x-intercepts. And you set those factors equal to 0, solve for x, and that is where you have an x-intercept, and that is a point on the graph that the function goes through. So that's all x. Then we switch gears to y, which is range and horizontal asymptotes. Horizontal asymptotes are places of discontinuity or long-run behavior in the graph associated with the y-axis. So horizontal asymptotes, y-axis, up and down. And for this, you're going to focus on the degree. Remember, degree is associated with end behavior. And so that's focusing on good old dance. Remember that? So I had a little memory device here in a previous video, Bobo, Botu, and Betsy, my friends. It's just a memory device to help steer you in the right direction for where your horizontal asymptotes are. And then once you find that, you write it as an equation of a line because it is a line, y equals whatever number it is. And that has to do with the degree of the function. And I'll show you an example, so don't worry. And then y-intercept. The y-intercept, if you think about all the times we've looked for a y-intercept, that is the y value when x is 0. So if you plug in 0 to all the x's of a function, rational function, then basically, long story short, you're going to be left over with the constants. Remember, the constants are values, numbers that don't have a variable. So the y-intercept is the ratio of those constant terms written as a point. And then last thing I'm going to go over is Botu. This one, the memory device kind of falls apart because U stands for undefined in the memory device. So it's not actually undefined. It's kind of more of like a unknown. And basically what that means is that if you end up with Botu in your horizontal asymptote, that means it doesn't have a horizontal asymptote. It has a slant asymptote or oblique. Those mean the same thing. And in that case, we have to do a little bit more work. We're going to have to do long division or synthetic division, depending on the function. So that's a lot of information, a lot of summary, but I'm going to go over everything you see on this page. You're going to see an example of everything that I've gone over. So let's just get started. I have a function, h of x. It is the ratio of 2 polynomials, f of x, g of x. So that's just definition of a rational function. You don't have to worry about that. And then it's written out as 2 times x squared plus 9x plus 18 over x squared plus 3x minus 18. The first thing you really want to do so that we can really see what's going on here is just go ahead and factor the numerator and denominator. And for the sake of practice, just pause the video and factor it yourself and then come back and check it. So remember, when you're factoring, you're looking for, in the numerator, factors of 18 that add to 9, that's 6 and 3. In the denominator, you're looking for factors of negative 18 that add to positive 3. That's going to be a positive 6, negative 3. So that's factored. Right off the bat, we can see that there's an x plus 6 in the numerator and the denominator. These will divide. And remember that when something divides, that indicates a whole. So I'm going to go to the whole. I'm going to go ahead and write x plus 6 right there. So I don't forget it. It's right there, front of mind. And then that leaves, so this is a whole. That leaves what's remaining in the denominator, the vertical asymptote. So the factor that remains is the vertical asymptote. And we'll come back to that and we'll solve them. But for now, I'm just writing it down because I can see it easily. And then what remains in the top, so I'm gonna label this vertical asymptote. What remains in the top, the numerator, is an x-intercept. So I'm gonna write that down. So I've got some really important pieces of information written down, and I'm gonna be able to see a lot about my graph based on that information. And then domain, remember, domain is denominator. And those are the values that have to be excluded from the denominator. Basically, these values make the denominator 0. And when we have 0 under, that's undefined, and that's a problem. Places of discontinuity. So those two factors, we have 2 in this case. And remember, one of them is a whole, one of them is an asymptote. Now, it won't always be that way. You may have 2 asymptotes, or you may have 2 wholes. I don't know. But in this case, we only have 1 whole, 1 asymptote. So with those values that have to be excluded, I'm going to set them equal to 0. And sorry, I should say for domain, it can't equal 0, because if it equals 0, we get discontinuity. So I'm going to minus 6 on both sides here. And I'm going to add 3 on both sides here. And I have my 2 excluded values. These 2 excluded values are places in the graph that are skipped over. They're places that are undefined. So if I were to look at a number line for this, I'm just focusing on x in this particular example. So I'm just going to do an x-axis here. And then I'm going to put negative 6 and 3 on my number line. Doesn't have to be exact. I'm just trying to show you an example. We would have places of discontinuity at x equals negative 6 and x equals 3. Technically at negative 6, it's a whole, but for the sake of this part of the problem, I'm just putting it that way. So I've broken my graph up into 3 regions. This points into negative infinity. This points to infinity. I've got 3 regions here, 1, 2, 3. And those regions are where the graph can exist. The only places where that graph cannot exist are here and here, as far as x. We're just talking about x. So this sets up my interval notation. The far left region represents negative infinity to negative 6. And then that break in the graph means union. Then my next region goes from negative 6 to 3. There's a break in the graph, so I need another union, 3 to infinity. So each interval corresponds to one region of the graph, and that's domain. So it may ask you what are the excluded values, or it may ask you for interval notation. And in this case, I've got 3 different intervals because I have 2 places of discontinuity. Again, you may sometimes have only 2 intervals. It just depends on the function. But in this case, I've got 3 intervals. So then I can go down to the next part. I have a whole at x equals negative 6. I have a vertical asymptote at x equals 3. And then I have an x-intercept at -3, that's a point. And I've done everything I need for X. That's all have to do with X. So I can go to the graph now and I can go ahead and put these pieces on the graph. For the whole is technically a point. So if you needed to find, which you do, if you need to find the Y coordinate of this whole, then you take the X coordinate, plug it into what's remaining, and that will give you the Y coordinate. So go ahead and try it, come back. Sorry for got a little messy, a little cramped here in my spacing, but I don't believe in the homework it's going to ask for the Y coordinate, but just in case it does, there it is. You plug in the X coordinate to the remaining factors and then simplify, and we get a third here. So we have a whole at -6, 1/3. So I'm going to go over to -6, and it's going to be a rough estimate because a third's kind of, that's really rough, but you get the point. -6, 1/3, I have a literal open circle there. And then I have a vertical asymptote at X = 3. A vertical asymptote is an imaginary line. So this is the equation of that imaginary line. Now, if you're looking at a calculator, you're not going to see anything. You're just going to see a jump in the graph. For this on paper, I'm going to do a dotted line or a dashed line, just so that I can show the reader or whoever's looking at this that there's a jump in the graph. And then I have an x-intercept at -3, 0. So I've plotted everything that I have so far. Then the next thing, the y-intercept, is if x is 0. So if x is 0, then what remains is 18 over -18, the ratio of the constants. That simplifies to -1. Now you might have noticed that there's a 2 out front, and that might freak you out. And you might have noticed I didn't include it. You can include it if you want to, but basically what would happen is you'd have 2 times 18, 2 times -18, and then it would just reduce in the end, so I just skipped a step. So the y-intercept as a point, our x value was 0, our y value is -1. So then I can go right here and put a point. And we're starting to see the shape of the graph. You might be like, I am not seeing it, but I promise you, it's coming. We're getting very close. The horizontal asymptote is also called long run behavior. That is based on the degree of the function. So if we go up and we look at the unfactored form, that's why it's important to have both forms, because we need the factored form for all the X stuff, and we need the unfactored form for the Y stuff. So if I look at the leading terms, and I focus on the degree, the exponents on those terms, they are the same, they're equal. So this is a case of Betsy, bottom equals top C. C stands for coefficient. Now I have that 2 out front, so I do need to consider it for this. This will be a 1, this will be a 1. So the coefficients of the leading terms are 1s, but there's the 2 also. It's kind of hidden. So the coefficients are 1, and simplify. So our horizontal asymptote is at y = 2. And it is a line, so I have to write it as a line. Then go to 2, put your dashed line, and now we can really see what's going on here. If you're unsure, if at this point you're unsure what the graph looks like, you could plot a few more points, just pick some X values. I would recommend some of these X values just to figure out where the rest of the graph is. but rational functions are symmetric. So it's going to mirror what we already have. Right now, what I have is boundaries, boundaries here. I know I cannot cross those lines. They're boundaries. And I have points here. So if I follow the points and I follow the boundaries, it's going to go through those points, skip the hole, and then it's going to get really, really close there and really, really close there. Never touch, but get really close. So just going to do a sketch here. Doesn't have to be perfect. Oh my goodness, really not perfect. I tried. Go down like that. And then it's going to have a mirror image here. Again, it's just a sketch, not exact. So I could use a table of values and get more points to get a better idea. But that's what it's going to look like. So let me zoom out so you can see the whole thing. That is our first rational function. Just to give you some reference here as far as a table of values, I went to y equals and I put in the function, and then I went to table, and there's some points that you can plot. At 3, you can see it's a discontinuity, which checks out. And then 4 goes to 14, 5 goes to 8, and you could get a better graph there. So there's that. Next one, now that I've walked you through one whole problem, one big problem, I want you to try and get as far as you can on this one. Pause the video, go ahead and try it yourself, come back and check your work. So for your first step, you want to factor the numerator and the denominator. So for factoring in the numerator, it is not a quadratic, but there is a GCF, so we pull out that 2. And then in the denominator, we're looking for factors of -7. Uh-oh, I see a mistake. Sorry about that. Factors of 7, -7 that add to -6 would be -7 and +1. And then that sets up our denominator, or sorry, our domain, which is associated with denominator, but there are not any holes in this case, nothing divided. So in the whole section of this problem, there are none. So you might say does not exist or none or NA, whatever. And then for vertical asymptotes, that means that both factors in the denominator are both vertical asymptotes. So I'm going to have 2 imaginary lines in this case. And all of that is associated with domain. So you set your factors, they cannot equal 0. Go ahead and solve them. You should get 7 and -1 as your excluded values. Then you can do your little number line over here with your asymptotes, and that sets up your 3 different regions. When you write it in interval notation for domain, make sure you put it in order, smallest to largest, just like that. So over here on the graph, that means we can put our asymptotes. We had +7 and -1. And then our x-intercept comes from the numerator. And you can do unfactored form or factored form here. If you divide both sides by 2, you get x minus 4 equals 0. Add 4, write it as a point. So I go over here to 4, 0, and I have my first point on the graph. Then the y-intercept is the ratio of constant terms, because the y-intercept is the point where x is 0. And when you plug in 0 to all the x's, you end up with just the constants. That's why I skip to the constants. And then you write it as a point. So that's just a little bit above 1. I'm just going to estimate here. I can get close enough for a sketch. And then your horizontal asymptote is based on the degree. In this case, we have the leading coefficient, or term is 2x. and the leading term is x squared. This is a case of bigger on bottom because of the squared. And bigger on bottom is Bobo. Bigger on bottom means y equals 0 is our horizontal asymptote. Okay, now when we go look at the graph, you're going to be like really confused for a second. You're going to be like, I thought that was an asymptote, and you can never touch an asymptote. For horizontal asymptotes, I have in parentheses long run behavior because there are some cases like this one that it does go through the asymptote, but long run behavior indicates that there is an asymptote there, and I'll show you. So don't worry, just bear with me. Don't worry. But I do have an asymptote at y equals 0. And as you can see, my issue, I also have a point there. But you will see as we continue to graph what's happening here. So if you're having a little bit of a hard time figuring out where the graph is going, because like in this case, I've got some boundaries, but I also have some conflicts here. And I'm not really sure, am I going to graph up here? Am I graphing down here? I don't know. We don't know. So in this case, it's very advantageous to go ahead and just do a table of values. Just pick a couple X values that kind of give you a better idea as to where your graph is going. I'm pretty sure there's going to be maybe like a cubic function happening here. But after that, it's like, not sure. So you can do a table of values, plot some points, and that can give you a better idea. So go ahead and pause it. You can use your calculator. Go ahead and pause it, do a table of values, come back and check your graph. So what I'm seeing is confirmation that I've got a little bit of a curve right here, and it's going to follow the boundaries down. And then I plotted some points over here that are also going to follow these boundaries. And remember, it's symmetric, so I don't really need to plot any more points because I know that it's going to be a mirror image in the diagonal region over here. And it is just a sketch, so I can just sketch it, or you can look at some points over there. You can see it 8. It's in the positive quadrant, so I know that it is in fact up there. So rough sketch would look like that. If you're getting confused with all the dotted lines and everything, you can always just go to graph here and you can see maybe a little bit better what's going on. And you can see, let me do this here. And you can see that the long run behavior does have that asymptote at y equals 0. So you can see as it goes out towards infinity, long run behavior, there's an asymptote. So there you go. That was a fun one. I like that one. I like tricky ones. Okay, last one. I want you to go ahead and start it. If you're overwhelmed by x to the third, you might use a table of values to figure out where those x-intercepts are instead of trying to factor it. So go ahead and factor all that out and find all the pieces and come back. If you look at just the numerator and you plug in the numerator to y equals of your calculator, go to the table, then you will find x-intercepts at -5, -2, and 3. So we can write that in factored form using those roots, those x-intercepts, as x plus 5 times x plus 2 times x minus 3. And that's how you factor easily. And then the denominator, we're looking for factors of -2 that add to 1. We get +2, -1. And now we have our function is completely factored. And then I've got it labeled here, which is going to help me kind of figure out the rest of the problem. But we do have a factor that divides, and that makes it our whole. And then we have a factor remaining in the denominator that makes that factor our vertical asymptote. And then the two factors in the numerator are our x-intercepts. So we have two x-intercepts in this case. So I put that all down here. I'm going to go kind of quick because we've done 2 examples already. So hopefully you can follow along. Remember, the domain is denominator We use both factors in the denominator to set up our domain. We know that it cannot equal -2 or 1. Those are excluded values, which sets up our interval notation. Then I have the whole that was at x plus 2, so the x value is -2. Plug in -2 to the remaining factors of the function. Simplify, and we get 5. So we have a whole at -2, 5. And then we have a vertical asymptote at x equals 1. And we have two x-intercepts, one at -5, one at 3. -5, 3. The y-intercept is the ratio of the constant terms. Simplify, we get 15. That's way off the graph, but it's going to follow our in behavior here. And then this is going to be a little bit different than what we've covered, but I promise to cover all the things that you might run into. So when we look at the horizontal asymptote on this problem, it's a case of bigger on top. We had x to the third on top. And in that case, there is not a horizontal asymptote. But what that does mean is that there's a slant asymptote. And there's two ways you can approach this. You can do long division or you can do synthetic division. In this case, synthetic division works, and I think it's faster. I will show you both, but I'm going to start with synthetic because I like it better. So I have my factored function, and I have the factor that divides. And with the factors that remain, I'm going to multiply those together. And I get x squared plus 2x minus 15. And then in the bottom, I have x minus 1. With that, I can do synthetic division. And I've already covered synthetic division, so I'm going to run through this quickly. We have an x value of 1 based on the denominator, and coefficients of 1, 2, and -15 from the numerator. Draw your line. That'll be your remainder. For synthetic division, slant asymptotes, we are going to be focusing on this piece right here. I already know this is not a factor because it doesn't divide. I saw up here, it doesn't divide. So I am going to end up with a remainder, but I'm just going to ignore that for slant asymptotes. Bring down the 1, multiply, add, multiply, ignore. So this piece here is the equation of our slant asymptote. Super simple. And then remember that since we started with x squared and we divided by x, my new polynomial is 1x plus 3. These form the coefficients of my new polynomial, my reduced polynomial. So I can go up to the graph and I can draw a dashed line at y equals x plus 3. So this is a slant asymptote, and as you'll see, it's going to be slanted, so that kind of makes sense. Starts at 3 with a slope of 1. I'm going to do dots here because I think it's going to be easier to draw. Get a really good idea. Remember, this is just an imaginary line, so I did it dashed or dotted. And now I can see that I have graph here, and I'm going to have graph here based on my boundaries and my points. So your graph should look something like this. Not too bad. And then I promised you that I would show you long division in case you didn't like the synthetic division. Long division is going to involve the original polynomial and the original denominator. And I have gone over long division a little bit already, so I'm just going to kind of run through this again, like I did with synthetic. X squared goes into x to the third, x times, multiply that back out, that's x to the third, x squared minus 2x. Remember, we're subtracting this whole line like normal division. We get 3x squared minus 9x minus 30. X squared goes into 3x squared. 3 times, multiply that back out. That's 3x squared plus 3x minus 6. Really, at this point, I can stop because I have what I need, but just for the sake of the problem, I'll keep going. We need to subtract this line. So that goes away. That's negative 12. And that doesn't really matter because what we need is right here. That's it. So I could have stopped earlier, but that's it. So you can see with synthetic and long division that we still get x plus 3. That is it for slant asymptotes, and that is it for rational functions. So I hope you enjoyed the lesson. If you have any questions, please let me know. I'd be happy to help. See you in the next one.